Aldo is going to present an informatic platform called BigData Platform, and it is designed for image-based digital twins. And so Aldo is now at Onera, but it was previously as a postdoc in School of Mines at Centre des Matériaux. So Aldo, you have the floor.
Okay, so I think that everybody can see my screen. Can you, if you can't hear me, just tell it on the chat. So as David said, I was working in the Centre des Matériaux to develop the BigMeca data platform, and I'm now recently been hired at Onera. And so I will talk to you about this work that can be seen as the technical counterpart of the physical developments that take place in the BigMeca chair. And especially the focus will be on a data platform for multimodal 4D mechanics of material microstructure, and particularly polycrystalline materials. So, okay, I will go into 5 parts. I will first introduce the opportunities and challenges that we have to meet with this data platform, and especially explain why we need a data platform. And I will briefly review some examples of the literature of data platforms that have been built by other communities, and also for other types of material science research. And then I will present the data platform that we built in the PMicro Python package that was mentioned by Clément. And finally, I will present the technical aspect of the construction of the polycrystalline datasets that Clément is gathering for its PhD before concluding my talk. So the first thing I want to mention, and I already talked already about this, is the rise of even always more sophisticated automated techniques that allow you to characterize now the mechanics of microstructure at very fine scale, and that can be also 3-dimensional in time, so in situ 3-dimensional characterizations that allow to image phenomena such as damage or microplasticity. So you have already seen the example is the slip bands that have been imaged by topotomography by Henri, thanks to the stress rigs that can go into the synchrotron. Stresses and strains inside grains can also be measured by high energy diffraction, so the same technique but slightly different processing method. And now we can also stress the importance that microscopy has taken by SEM analysis that can now be very powerful, very automated, and that are getting coupled now with other modalities to build multimodal analysis of one specific phenomenon, such as, for instance, here a study by Spirial in the US on slip bands. So they've characterized slip bands by carrying high resolution in situ DIC. They also use atomic force microscope to measure the steps at the slip bands and couple that with electron channeling imaging to see the dislocation structure associated. So we can have a very rich description of the phenomenon at very fine scales into 2D, 3D with more and more automated setups that promise to deliver a huge quantity of data that a lot of physical meaning. In parallel, we also see a lot of advances in microstructure modeling that is driven by the progresses of parallel computing. So mainly for FFT-based and finite element methods-based solvers, where we can see microstructure sensitive simulations, so that can represent the microstructure at a very fine scale for various phenomena, including plasticity, damage. So here you have 2 examples. Here is a simulation of localization of slip localization within grains, or you also have here a work that was conducted by Yang Chen under the supervision of Lionel, which is a direct computation carried out with FFT-based methods on a tomographic image of a 6-sig tube, braided tube, that allows to compare the observed damage with the stress concentration that were calculated with this technique, really at a very fine microstructural scale. You also have a simulation that can use advantage of reduction techniques to perform a lot of cycles. And so even for complex simulation problems like the cyclic plasticity, we are getting into having local descriptions with models. So this opens two roads. The first is local basis, as was pointed out by the question, David's question in the previous talk. But also, if we trust our models to enrich experiments with simulated data that can complete what cannot be measured, and so build multimodal data sets, not only by accumulating experimental techniques, but also adding simulated data into the data sets. And finally, we can also mention machine learning based approaches. So this has been presented by Henri, so I will not detail it, but that can take advantage of this simulated data and experiments to train and also be able to provide infrastructure sensitive simulations. So they can both value the data that we can generate and also help to train them. So what we can do basically is now take benefit from all these techniques to study maybe one sample or a few samples with all those modalities and be able to get unmatch the level of description of the physics at these scales. So that's the program for the next years of infrastructure research. But for that, we face the data challenge that Henry mentioned. So especially there is the first aspect is the multimodal and large character of data. So multimodal means that you have data coming from many technical modalities, but that also have different natures. So EBSD, DCT are coming from different physics, so they have different geometrical forms, different meanings. So that's one first difficulty. The same for simulated data. So maybe a deformation field from a solver will not be exactly the same meaning of one that can be measured. So we have those kind of problems. And we also have data that characterize models. So if you think about machine learning models, they have lots of parameters. So it's a large quantity of data. They also have constitutive laws that are characterized by a few parameters. And all those data comes with different data formats. So encodings, ordering, different file formats that have specific technical conditions, compatibility conditions. You have also a lot of spatially organized data because we deal with microstructures. So the geometry is at the center of all of what we do. And so the conventions for ordering arrays, dimensions, their frame to be sure that you can geometrically align your data. All this is also a source of challenge because it adds technical complexity to the manipulation and the comparison of or the cooperation of multimodal data. So as people the rest, you also have an important aspect that was already mentioned is the size of datasets. So microstructures data are large. You need multiple gigabytes to store mechanical fields and microstructure maps for the size of the microstructures that were discussed earlier. And that needs to be solved with efficient storage and input-output pipelines. So those are that's the first challenge. And the second challenge is to allow for the convergence, the cooperation of all these data. So what we want to do basically is conduct this kind of methodology. So Clément is working on the two first steps, so accumulation and processing data from multiple sources using multiple tools. And then we may want to value this data through the training of machine learning algorithms or reduced order models to be able to deliver statistically representative model of fast mechanical precision or quantify uncertainties due to microstructural variability or such this kind of mechanical studies. And that needs a lot of data transfer that are symbolized by the red arrows here. So as you can see in this scheme, you have a lot of arrows, and each arrow is a technical conversion, is a technical operations that needs some knowledge, informatical knowledge, knowledge on the numerical tools. And so you can quickly see that for one person like Clément conducting its PhD, it's become rapidly intractable to have this burden to take care of. So the idea is to build a data platform that will solve these problems by removing all this technical complexity by simple commands like the one that are symbolized here in the red rectangles. So add, remove data easily, visualize data easily, and automate processing pipelines with all the tools mentioned earlier to interact with both data sets and models that help us to do our science studies. So these problems, of course, are becoming urging now in the material science community, but have been met by other communities before. And so we started by reviewing quickly what they did. And I will focus here mostly on the most advanced ones that have been built by the astronomy community. So they're called virtual observatory. So they're driven by one organization, the IVOR, International Virtual Observatory Alliance, whose role is to debate and promote data standards that include data formats and exchange protocol, and that are the base of all the tools that they develop. So they agreed on those formats, and all the tools that the organization that adheres to the AVOR develop are developed according to these standards. And so this has allowed to build a platform like Aladdin here, which is an interactive sky map, an interactive sky atlas, where you can have a web-like universal access to observational datasets, where you have shared visualization and processing tools that allow you to, for instance, select a few objects here in the sky and get all the measures from all the years that have been operating, that they have been operating telescopes at various length scales, and get all this data easily, even process it using an ESA tool. So you have also this kind of platform that has been developed for Earth science. So you have here the Earth observing system that's developed by NASA that relies on the same principle. And that's an example of an image from that can be queried on a virtual observatory dedicated to the sun. So you just have to click on a few regions and you can access multimodal data of anytime you want, or the opposite, you can search the region that needs match some data. So obviously this is a huge accelerator for the astronomers that want to focus on one specific phenomenon. One aspect that is important is that they manage to do that even though they have a high multimodality of the material. So if you think about all the telescopes, all the wavelengths that are studied by astronomers, you quickly get the level of multimodality that are dealing with. In material science, a lot of initiatives have been triggered recently to meet the challenge of integrated computational material engineering, which ultimately aims to develop an integrated platform that allows to simulate all the properties of a material online, or informatically, and to be able to speed up this process, to speed up material development, and especially reduce the cost of experiments in the development. So we can quote the Material Genome Initiative that has financed a lot of projects, including, for instance, AFLOW, that is a database for the study of the relation between material composition and physical property that is done through ab initio calculations. And so they have created standards to automate these simulations, store them with the standard formats, and so they have computed hundreds of thousands of properties for various compounds that you can query online and access like an open database. So you have powerful tools, once again, to find the material that match your needs, or the opposites, to get the property of a material easily, which will speed up the material development time. And one initiative that has particularly interested us is the Dream 3D software, which has set the ground to work with the digital microstructures. So it's set up a format and also provide the pipeline. Like you can see here, it's a graphical interface that's really simple, where you have human understandable commands that can be understood by any scientist, that doesn't require technical complexity, and allow to automate reconstruction, generation, microstructure statistics for data that come from 2D or 3D microstructure characterization. It has recently been changed with computational plasticity tools like the Prism platform. So what does all these efforts have in common? Well, two important points, data formats and data standards. So the data formats that they use includes the shape of data and the file formats that they use. So they have in common to use hierarchical and flexible formats. Hierarchical means that you can organize the data items in your file with links and create a hierarchy exactly like a file system within a single file. So you can organize your data sets. This is schematized here where you see branches that ultimately are like a tree in a file system. And they are flexible in the sense that you can design according to your needs this hierarchy and add more or less the fields that are required to build the standards. So this is one part. The second is that they set up standards on the shape of data. So for instance, Dream3D proposed to store microstructure as grids. So basically a set of points and a set of cells that are defined like a mesh or an image, and that defines the geometry of the grid and that are the supports for microstructural data. But you have other conventions, of course, for astronomy or oceanography, which have set up similar conventions to organize data dispersed in the sky. So one file format that is widely used to do this is the HDF5 formats, which meets the criteria to be hierarchical flexible, that has no size limits, that can be self-descriptive in the sense that it can add metadata for all its items. It's widely used, it's supported by a powerful library, and also allows to use strong data compression algorithms, which is mandatory for us as we deal with large amounts of data. And all those standards are shared and are discussed and then officially published by these organizations. So that's a very important point. And then those standards and formats are supported by user-friendly interfaces that allows like the pipeline here to use it, even if you don't know anything about the technical complexity of the data formatting. So now we try to go towards this way, and we develop a data platform in the BIGMECA Python package. So it's a package that's developed by initially by Henri to deal with polycrystalline datasets. And so we've enlarged it to include the data platform. So essentially, the data platform is the conjunction of data formats, the data model, and this Python package. So the data formats is a form of a dual data format. So we took the HDF5 format as for the reason I mentioned earlier, and we couple it with the XDMF formats, as the XDMF format can be directly visualized into Power View. So provided that we get the two files synchronized, we can have a very powerful and free visualization software at a free cost. So that's why we chose this solution. Then the generic data model is an enrichment of the data model of the HDF5 model, which I will present just later, just after, which allows to create with flexibility the multimodal dataset that we need. And that also includes a data standards design mechanism that I will explain very briefly. And all this is handled by a Python package that also serves as interface for now with datasets. So you can interface with datasets to interactive Python. And it also pilots interfaces with external tools. It's easy to use, and it's built around a central class that represents datasets. So the sample data class whose objects are the datasets. So I have to mention here, of course, that the package uses the Safran basic tools package for all the problems linked to mesh manipulations. So the data model, I will not go into the details of the elements as I will later, but you recognize the study of Clément, is composed of three different kinds of organization level datasets, data items. There are groups. So group is like a folder in the file system. And so you have generic groups that can store any kind of data. And we created image and mesh groups that are groups that includes data to represent the topology of a grid that is a mesh or an image. So I won't go into detail, but there are specific topological properties that need to be dealt with separately to optimize treatments. Then we can also store a structural table, which are like those light blue tables that can contain various fields. A set of rows that are various fields and that are uniform. So it's very useful to store function statistics. We also can store fields that are data arrays, but specific special organizations that meet the convention of our image and mesh groups. So we have image and mesh fields. And we can also store a simple data arrays and metadata that you can see in orange. So the mesh, the data standards generation mechanism that I mentioned here is symbolized by the red stars. So basically, there is an easy mechanism to develop by writing simply a list of elements with an associated path, data standard, data model, that will give you a family of objects or data sets that will automatically be generated with the hierarchy that you design providing this list. So here we just provide the path and the names and types of the groups that have a star, and all the data sets, so the polycrystalline data sets family that we will generate will be automatically created with this organization, which allows you to control the minimal structure of your data sets and have a base standard and a base brand to work with other scientists through a simple definition as a Python list. The interface to interact with these data sets, as I said, for now, it's interactive Python. So you have a simple methods that are very explicit in their names, like get information on one node, and you have explicit sprints that give you all the technical information on the grids that are stored. So here you have, for instance, field, so you can see the grid is related to its name, its type. And here is a scalar field. It could be a vector field, a tensor field. It's an element field. It could also be an integration pole field. You have all of this kind of information that are given. You can easily create data sets. So basically the commands are add image, add field. So it's really explicit. And the same for basically all the functionality, compression, interactive visualization. So the idea is that those methods could be easily mapped into a graphical interface and becomes patterns in the future. You have also two examples here of visualization. So we have here the visualization of a mesh that has been generated automatically on a tomographic image of a hollow sample. So two different modalities that have been superimposed and visualized into pair views. That allows to confirm the geometrical alignment and ease and facilitates the work with different geometric modalities of your study. And you can also use other tools like tables and sticks to observe the structure of your data set in a very similar aspect as file systems. So I won't go into the too much technical details for the coupling with external tools, but basically we use another class that generates templates and runs external programs to ease the development of interfaces with other tools. And so we were able to automate completely through the platform the use of the automating meshing tool mentioned by Henri that was developed by Franck Nguyen, that can mesh any two-dimensional or three-dimensional multi-phase image. So an image with a set of labeled regions. And so you just use one command, providing a few options, and you get a mesh that are also already stored into the data set that then can be visualized immediately with ParaView, and it's geometrically aligned. So that's one of the things we were able to achieve with external tools. So to give a more interesting example, so we took the microstructure that was presented by Clément in his second example. We extracted a subvolume of 200 cube voxels, and we meshed it on the Centre des Matériaux cluster crystal. So that's the result that you have here. It all takes this takes only 5 lines of Python that are rather easily understandable. So that was the goal of the development of the platform. We also did this on with the ZSet finite element software. So I won't go into too much detail, but here we have an example of an eigenmode computation. So providing a strange structure that actually represents the uncertainty zone of the reconstruction of a PCT sample. So that's in red, the zone where we are not sure where the grain boundary are. And then we just mesh it with the Frank algorithm. Then we send it to ZSet. We set up a few boundary conditions, loading conditions, and then we compute the eigenmodes with, so not one line of Python, but the tens of lines that are really closely mapped to the commands that you would give to the ZSet sample. And once again, this is all automated to the platform. So all the data that is generated is generated into the data set and is geometrically aligned. And so you can visualize everything on Power View very quickly. Now, the application of all this work, for now, the most advanced one is the work conducted by Clément. So we'll briefly review the context, as is already you already had a full presentation of it. So it's an in situ multimodal study of commercially pure titanium that associates synchrotron DCT characterizations to in situ SAM technique testing, and that is completed by FFT crystal plasticity simulations. So the goal is my goal at least, was to demonstrate the technical feasibility of assembling such data sets and such workflow for a data set of thousands of grains, as Clément showed. So showing that it's easy to do in a reasonable time with this platform without any expert knowledge of, once again, the data technical aspects. Of course, you have to be an expert of polycrystalline physics. Okay, so the scientific focus of this work, if we have to get one saying point, is the statistical comparison at the grain scale of the crystalline rotation that are both simulated and measured. And that's what the data set is meant to. So you have seen the workflow presented by Clément. Here it's summarized, and the emphasis is put on the data exchanges and the different tools that are used. So the black lines represents the data set that grows throughout its construction. And above in blue, you have all the external tools and external steps. And below the line in orange, you have all the tools that are fully automated through the platforms. And then all the the orange arrows represent data flow that are fluxes that are completely handled by the platform with a command that is 1 or 2 lines of Python, as I showed earlier. So the microstructure characterizations provides maps of the microstructure, some outputs that, as Clément said, has been morphologically cleaned, and grains have been dilated. There have also been microstructure statistic computations to get geometrical parameters for all the grains in our microstructure. And all of this is automated into Timicro and can be done in a few lines. So then everything is automatically stored into the data sets, which is then ready to get the scans from the in situ SAM tests. For the meshing, it's the same. You press a few commands, and then the dataset sends an image to the mesher that's come back with a grained polycrystal. It's the same for the computation of orientation deviation maps and the statistics that Clément showed. And for the FFT-based simulations, so the process is not fully automated, because to run this simulation, we have to go through a job manager, a parallel job manager for HPC cluster. So we haven't automated this yet in the platform, but the input creation for a polycrystalline microstructure and output fields storage into the the data set is automated. So you just take the output directory of Amitech and all the statistical and spatially organized outputs, and also of course, the macroscopic curve is stored. So that's what we were able to do in like a reasonable file of Python with the platform, or you can imagine 3 or 4 very short scripts that can implement these data sets at the end of the process of development of this platform. So I show you again the data set, and you can see that it's organized to gather all this data into a logical and easy to understand and navigate hierarchy, and that you get your statistical information that's per grain that has been computed from the simulations with, for instance, the lattice rotation here. That can be directly compared to the statistics that would be extracted from those fields once they will be computed for the several steps of the in situ test. And so we will have directly the possibility to compare them, compare the fields, superimpose the results, align the 2D and 3D characterization with a very simple interface, which wouldn't be possible or would be very complicated technically to do without all this technical infrastructure. So I will end my talk now. A few words of conclusion. So what we have developed in this chair is a functional open source data platform package that is suited for multimodal material mechanics. I insist on multimodal mechanics because there exists data platforms to work with microstructural data, but that are not that don't put the emphasis of gathering also other modalities of imaging and simulations and statistics and so on. We showed that the multimodal workflow can be simplified and automated using this data platform for both the creation of interaction with datasets and also the use of external tools. And this has enabled us to assemble a large dataset of to study the microplasticity of titanium by decreasing a lot the technical complexity of the task. So a few words of outlook. What I want to say is that for this platform to be even more useful and powerful, we need use cases. Henri mentioned that we need to do tens of samples, tens of experiments. So that will allow to get more workflows toward the platform. What would be really interesting to spread it is to have more tools integration, a graphical interface, maybe a web service to access it online. This has been done for the platform I presented earlier. Maybe enhance the convergence with the platforms like the Dream 3D platform or other computational platforms. And as Henri mentioned, it's to deploy it to HPC facilities and on beamlines to directly format the data from the tools that we use with this formats to speed up the processes. Then we can say a few, I mean, it would be interesting to develop database functionalities. So for now, it's not pressing because we are at the stage where we are constructed the datasets one by one. But once we will have a lot of datasets, we will need database functionalities that can be powerful even if the datasets are very large, because with HDF5 files, you can access information in the file without reading the whole file. So you can imagine efficient database functionalities. And then one important point is that those standards, I mean, we need standards that could be implemented using this platform that needs to be discussed at the community scale. So in order to unite the efforts into this direction. So I'm done with my talk. Thank you and for your attention, and I'm ready for the questions.
Thank you, Aldo. It's time for questions. Yes.
And this is not something we need to
Well, there is a report that I've done on the literature review that may help in this direction that I think we can share. The platform documentation is online, so it can be seen online. And so that's it. You can see the code, you can see the documentation of the platform. I want to stress the fact that we didn't propose a standard here, but we proposed a framework to implement one if there is one that is developed. So basically, of course, we proposed a data model, a concrete one, because we had our needs, but it's free. I mean, it's free. It's flexible, so we can design any kind of data model that we want with our platform. And so it's only a matter of agreement to implement something in a more hard way, using our tools. But that wasn't our goal. So the discussion must be open now. So I don't think that our efforts will help set one standards, but it provides the tools to be able to do it quickly and efficiently, in my opinion. Mm.
And we agree with most of the one of the other things we followed was that first was the separation between DDFI and DDFI, which we can each interact with the DDFI. And some of those possibly have access to the DDFI API. At some point, when it becomes quite big, as is probably your case, the definition of the information is more of a terminal than an actual event. Is it something that is very much as well? Or are you still confident that the beginning of as it exists is robust?
So what kind of trouble did you encounter?
Typically, the cycle grid is stored both in the HTML as an actual physical length.
Mm-hmm. Yeah, well, I think that the way to go is to focus only on the HDF5 file, and as I see it, we only use the XDMF extension, so it's better to say extensions to get the ParaView compatibility for now in our needs. So maybe we need to work on a plugin that allows to read the grids that are formatted like this from HTML5 file. I mean, it's the same thing. If it can get the information from the XDMF, it could get it from the HTML5 file because it can read it. So maybe that would be the way to go. But to avoid problems, that's one thing that we are working on. For now, the files are synchronized, so you can have problems with duplications, synchronizations problems. But the idea would be to build the XDMF file only when you want to visualize it, for instance, from the information that are in the HTML5 file, which can be done easily from what we have developed. So that would be my answer. Focus on the HTML5.
Maybe I want to comment on this on the first question about the data standards, because it's indeed a major point. So we've done, as mentioned, Aldo mentioned a proposition, and we have more of a platform to implement any data standard. But we recently submitted a big European project for all the synchrotrons and X-spheres in Europe. And we proposed BIGMECA to be the one of the. So this project is on building a digital twin of the synchrotron, basically. So from the source to the sample and the detector signal and so on. And BIGMECA was proposed as the tool to do this for the sample. So we hope to benefit a lot from this if the project gets funded, because this is going to be a huge infrastructure, and we have to go through data standards. So maybe we have some more on this in the coming year or two.